So I think it's time to start again. So thank you everybody to be here. I have the pleasure to present Miguel Escobedo. Miguel works at the Department of Mathematics at the University of the Basque Country, and he works in the study of nonlinear partial differential equations, existence and uniqueness of solutions and their qualitative behavior using tools of classical calculus and functional analysis. He has been more involved recently in kinetic equations and strongly motivated by physical phenomena. So he's going to talk about instability of some equilibria in a homogeneous Boltzmann equation for radiation. Thank you, Miguel.
Thank you very much for the invitation, for the presentation. Can you see the?
Yes, the slides, yes.
The slides, okay. So the first thing is, all right. So it's a pleasure and a privilege to participate in this conference in honor of Enrique. Of course, almost everything has been said about Enrique, but anyway, I can't. I can't. Okay. Okay. So I don't know if you still hear me, but I had some.
We hear you, but we don't see the slides move. It's
yeah. So I had a small problem, but I think it's working. So I was saying that essentially, well, a lot of nice things have been said about Enrique, but I would just like to emphasize the fact that Enrique's generation came after a brilliant Spanish generation of mathematicians who, as I say, started a new time for mathematics in Spain after a difficult period. And that sometimes is difficult, okay? But Enrique, as we all know, always did very well, always did as well as people before, and quite often he did much better. So that's something I would like to emphasize. And of course, Enrique is also a wonderful and generous colleague who enjoys tough discussions, not only on mathematics, but on other subjects. So for all this, I want to thank Enrique, wish him a happy 60th birthday and tell him sorry, So I would like to describe some recent and still partial results on a very simple, at least simply looking kinetic equation that some people call the Compton-Boltzmann equation. So it comes from a Boltzmann equation in three-dimensional variable, but after some reductions, it is simplified to this very simple situation. So U describes the density of particles called photons. It depends on T.
Slide, Miguel, sorry, we don't see the slide. You are at the beginning.
Can you see it when I
Only
move it?
the first slide. At least I don't see it moving.
Are you sharing your screen?
No, just one.
This is what you have to do.
Here it is. So here you have the Compton-Boltzmann equation.
Let's see if okay, I don't understand what is happening, but anyway. So that's the equation I wanted to talk about. As I was saying, U is the density of particles. and depends on t, the time. X is not a space variable, it's a momentum, an energy variable, and it will be non-negative. W is a function I will describe later, and small q of u is this quadratic form in u, or this nonlinear term in u, strange mixture that looks like something like in the Boltzmann equation. Okay. It was first written by companies in 56, and then it has been derived by many other people. It is described, or it was introduced to describe what is called the Compton scattering between electrons and photons, that are the particles whose density is u. And it is of great interest in many applications, plasma physics, cosmology, but also biomedical imaging, and in a lot of places where you have you need to describe radiation interacting with some kind of matter. And as it often happens with these equations, there's no rigorous mathematical deduction of the equation from the beginning. So I don't know if you see the new slide.
Yes, yes.
Okay. So this Boltzmann equation actually is mostly used in the applications because it has an extremely well-known approximation that is called the Companies equation, which is a diffusion, a kind of Fokker-Planck or convection diffusion equation that I wrote here, that was also derived by Companies. And it's the basis of what I call here the basis of the mathematical description of the Sunyaev-Seldovich effect in the cosmic microwave background. So it's a widespread model in all astrophysical books. You can find 1 or 2 pages about this Companies equation. Now, just from the mathematical point of view, the equation as one delicate point is how do you derive it from the Boltzmann equation? Okay, because essentially the idea is to expand the solution of the Boltzmann equation using a kind of Taylor expansion. And for that, you need the solution of the Boltzmann equation to have some kind of regularity. So you need to avoid strong gradients in the solution of the Boltzmann equation. So one of the first motivation is it always true that you can find regular solutions for the Boltzmann equation? Of course, a second problem of the Companies equation is that you can always find situations where you cannot use the approximation and you have to go back to the original Boltzmann equation. Okay. Now, about the function W. The function W is not trivial because the geometry of the collisions is not trivial. The photons are necessarily relativistic quantum particles, and the electrons, in order to get the simplest possible equation, are supposed to be classical, non-quantum, non-relativistic particles. So you are mixing things, and so the collision is not completely trivial. So W is like that, where omega is this integral depending on the angular variable of the scattering. And it has a delicate behavior at the origin. When X or when Y goes to 0, it is singular at the origin in X. And if X and Y go to 0, you get that kind of behavior. Okay, so omega it's not very singular, but it is singular. And that will be the source of some problems. Now, some general properties of the equation that are shared by almost all the Boltzmann or all the kinetic type of equations is the total number of particles, which is represented by this integral, the integral from 0 to infinity of x squared times u, is conserved in time. So when you multiply when you you integrate the equation for all the values of x, you get something that is constant in time. The energy is not conserved. It's different from the classical Boltzmann equation because we are not describing the electrons. The electrons are not taken into account in the equation. Only the photons are described. So when the photon, in each collision, say the photon is transferring energy to the electrons. And the equation has a set of equilibria, a whole family of equilibria, one parameter family that are given by these nice and explicit functions. Now here again we have two problems. The first problem that is perhaps the main motivation of our result is again related with the regularity of the solutions. In order to give sense to the nonlinear equation, we need to define the duality product of the integral collision with test functions. And in order to do that, we need to apply some Fubini argument. And here again, the regularity of u near the zero values of x is important. Moreover, taking into account that omega itself is not very regular. So we need to know, or we would like to know, what is the behavior of u when x goes to 0 in order to check that the weak formulation of the nonlinear problems makes sense. The second problem is more related, well, it's perhaps more related with the model, but it comes from the very striking observation is that all these initial data that I wrote before are all of them bounded from above by the equilibrium for a equal to 0. So by the total number of particles that you can put in the equilibrium for any a is bounded from above by this number and naught, which is the integral of this a. So in this model, a gas in equilibrium may only contain up to n naught particles. So what happens if my initial data, or if my gas initially has more particles than n naught? So do I have solutions? And if I have solutions, what happens to them when t evolves? So the case where the initial data is below one of these equilibria is more clear, because in that case, you have an equilibria to converge to. And at least the existence of solutions was proved by Ferrari and Nuri some time ago. But imagine that you are below UA for some A for almost every X, but you just have a small peak in your initial data, and the number of your particles is too large. So what happens then? So that's the motivation of the work I wanted to address. Now, what I'm going to do is try to use the simplest arguments. I am going to linearize the equation around the maximal equilibria, which is this one, and look at some small perturbation with a positive number of particles in such a way that I'm in that region where I have no equilibrium anymore, okay? So this situation happens for other equations. For example, if you consider the equation that describes interactions for boson particles with positive mass, because photons have 0 mass, so it's a very particular kind of bosons. But if you consider a gas of bosons with positive mass, you get a slightly different equation, more complicated. I don't want to describe it, but you have a similar situation. So there is a kind of maximal equilibria for which you can put a maximum number of particles, and you may wonder what happens. But in that case, what happens is that the equation admits another family of equilibria where you can have Dirac measures at the origin. And so you can increase as much as you want the number of particles in your equilibrium. So the question, the model admits singular equilibria, so equilibria with a Dirac mass at the origin, but you have equilibria. But in our case, in our equation, that is not, these kind of distributions are not equilibria in our equations. So even if the situation is not new, because it happens in other cases that you have a kind of maximal regular equilibria. In our case, the problem is that we do not have this singular equilibrium to solve the problem. So let me linearize around this maximal equilibria that I call 1 over exponential of x minus 1. I call it U0. And the linearization is made in this very particular form because it helps to simplify very much the way in which the linear equation is written. Okay, so the linear equation, I write it in that way, where Q of L is this integral, well, it's this linear term. Now, I have a multiplication by an explicit function, gamma of x, which is given by this expression. And here inside, I've this omega times the exponential of x plus y over 2 times y. This is kind of collision kernel in this simplified linear problem times f of y. So that's the linear problem. And what I would like to see is what happens if I take now an initial data, which is not necessarily positive. So the perturbation will not be necessarily positive, but the total amount of particles in the perturbation is positive in such a way that my perturbation increases the number of particles in the equilibria, and I want to know what happens. So the main result is the following. So I just need the spaces of functions that have some momentum x to the theta for theta positive. So there are kind of L1 spaces with weights, very simple weights. So my initial data will be a continuous function in 2 of these spaces for some weights alpha and beta. Alpha is going to be taken less than beta, but both of them have to be less than 1. Okay, so alpha is less than beta, so alpha less than beta, beta is less than or equal to 1, so alpha is strictly less than 1. So under these conditions, you can find a local mild solution of the equation for a small amount of time. The time is beta minus alpha, so since beta is already less than 1, this is a quite short interval of time. The function belongs to this kind of L1 weighted spaces. It is continuous in x and t for x strictly positive, and they satisfy a global, well, a bound for all time t less than the critical time, bounded by the norm of the initial data. Okay, so this k0 is a universal constant that doesn't depend on anything. So that's, I have a local solution for a small interval of time of my linear problem. And moreover, and that's the interesting point, I can get, you can obtain a lower bound, a lower pointwise bound on the solution f in terms of 2 non-local problems. So you have something that is that is singular at the origin, t over minus x times log of x. So when x is negative, when x goes to 0, log is negative, this is a positive quantity. You have here 2 constants depending only on the initial data. And here you have something that depends on the solution itself through the operator R that I will describe in a moment. This is a non-local term in X, and it's integrated in time. Okay, so that's the basic lower bound that you can obtain for X small and T small. Okay. Now, from this estimate, you can deduce the main result of the corollary, which is the following. If you assume, moreover, that your initial data is in L1, so it's not only in these L1 spaces with weights, but it is also in L1. And if you have a kind of condition that the whole integral of the initial data is larger than this weighted integral, so you see, if the initial data is constant, if the initial data is concentrated near the origin, this is always possible, okay? Because here we have the weights x to the alpha, x to the beta, so this will be always possible. So if f I'm worried about the connection anyway. If the initial data satisfies this condition, then the solution that we have obtained cannot be integrable in time and space in any small interval of space and time. Okay, so can you tell me if I'm still connected or if you look?
Yes.
Okay, very well. So if the initial data is in L1, essentially, and if I have this condition, meaning that the initial data is rather concentrated near the origin, then my solution cannot be in L1. So I claim that this is a kind of instability for the linear problem. Why that? Because no matter how regular and small is the initial data around the origin, if it satisfies these conditions, the perturbation, which is u naught times 1 plus u naught times f, cannot remain a small perturbation for times in 0 time, because this function, when x goes to 0, behaves like this function, taking into account the behavior of u naught and hyperbolic sinus, and this function is much, much larger than u naught because f is not bounded near the origin. F is not integrable, so f is very large near the origin. So the perturbation becomes much larger than u naught instantaneously in a small interval of time. So I cannot maintain a small perturbation for any small interval of time in my linear problem. So this is also not very good for the nonlinear problem, because for the nonlinear problem, in terms of the physical model, a natural condition of the perturbation is that this quantity contains a finite number of particles, because this is exactly the amount of particles I'm adding. If I want that to be finite, I know by a previous result by Ferrari and Nuri in 2006 that this condition will imply this condition, where I dropped 1 power of x. I go from x squared to x. But this condition implies that f is integrable near the origin. So if I want a finite number of particles in my perturbation, this implies that f has to be L1 integrable near the origin. So of course, I only have the result for the moment for the linear problem, but I strongly believe that this will imply that there is no L1 solution for the nonlinear problem, and that will mean that I cannot build a solution of my nonlinear problem containing a finite number of particles. So I will not be able to build a solution of the nonlinear problem respecting, say, the physical model. Okay, so that's the main result and the remarks I wanted to do. So what is the, how can you prove something like that? How do you obtain something like that? The idea is, oh my goodness. ¿Qué cojones pasa? No. Okay. So the proof has 3 steps. I think I will only have time to give 1 step, and 2 approximation. I think I will have time for 1 approximation, which is the main step. So the main idea is to approximate this function omega, which is complicated. Okay, the function of x and y is too complicated to solve it directly. So the idea of the approximation is to notice that if I drop the cosinus here, which is something made by physicists sometimes, then the remaining integral can be computed almost explicitly. So you can integrate this function. You get a kernel K for which you can know the behavior for r near 0 and r going to infinity. And you can also find very easily the behavior of the function gamma x that is in the linearized problem. So you may approximate the linear problem in that way, that I q tilde L, where I replaced omega by this function h, and where I replace gamma by this gamma naught. So h is a kind of Frankenstein approximation of omega. You see, it's 1 over r for r bigger than 1, so it's extremely simple. And for r small, I get something which only depends on y. So r will be x over y. Okay, so that's just a notation. So this is the kind of approximation I do for h. So what's the advantage? The very big advantage of this approximation is that you can solve it explicitly. This linear problem is the kind of skeleton of your problem, and you can linearize. You can solve it explicitly using Fourier methods, or in that case, Mellins transform method. So I Mellin transform the equation. I call it f hat with some abuse of notation. And I get this equation for f hat. It's a kind of linear hyperbolic equation, but non-local. So it's a kind of, well, but you can build an explicit solution, at least one. So S now is in the complex plane, but the real part of S is well chosen in order for this function to be analytic in some strip, and then you can take the Mellin, you can inverse the Mellin transform of this function G, and you get something which is horrible, but it's explicit or more or less explicit. Okay, so that's what I call capital phi. So you have 2 terms. One term still contains a Dirac measure. So that's a fundamental solution with a Dirac measure at y. At time 0, the Dirac measure is at y. So you still have a Dirac measure at y, but it's modulated, it decays in time, and you have this extra power of y. It's a kind of regularization, well, slightly regularization of. And then you have a function g, which is given in terms of some hypergeometric functions and binomial coefficients you don't want to know, and h is the Heaviside function. So you have 2 parts, one for x large. So capital X is small x over y. So you have one for small x large and one for small x small. Okay, so and this is the one which is dangerous because that's the behavior I'm interested in. What happens when capital X goes to 0? So when x goes to 0, you can give the asymptotic behavior of this function phi when capital X goes to 0 or goes to infinity. They are explicit, they are very simple to obtain. And the important point is that when X goes to 0, you get a 1 over capital X here, plus a logarithm. Okay, so it is not very bad, but it's not very good. In particular, it will not be integrable. Okay, so the function phi has a singularity. For X large, it's not bad. Okay, for X large, you get something that decreases. And as far as t is not too large, this will be integrable at infinity. But for X small, here you have a singularity. So now once you have the fundamental solution, you can solve the Cauchy problem. You can solve the Cauchy problem for a class of initial data that are still in that kind of spaces. You get a local solution, of course. You can define a kind of local in time semigroup, and you can obtain the behavior of the solution F in terms of the solution of the initial data. Well, I think I will have no time to give that. The second step, you start to add things to your kind of Frankenstein equation in order to get something more similar to the real equation. So the first step is to consider the function gamma instead of the function gamma naught. And so you get a second type of equation that you can also solve using classical fixed point arguments, and that you solve as a perturbation of the first semigroup. Okay, so when you add gamma instead of gamma naught, you get, for your first semigroup, you have an extra perturbation that you can solve in the equation. And using the explicit behavior of the first semigroup, you can find the behavior of this equation when X goes to 0 and for small values of t. Okay. You write your equation as a perturbation of the equation for the first semigroup. And then you can give the description of the behavior of this solution when t goes to 0 and X goes to 0 in terms of your initial data, plus the norm. So this is a non-local, but only for the initial data, plus the norm of your initial data, plus something that is arbitrarily small as t goes to 0. And now the last step is to consider the complete equation, okay, with gamma and omega. And again, you consider that as a perturbation of the second equation that you have solved. And so you put H here, and here you put the operator R that appear in the main result, which is just you add omega and you subtract capital H. Okay, so that is the operator R, which is well behaved for the spaces we're working on. So you can obtain estimates on this operator R when acting on these L1 spaces with weight. So you write your equation in terms of the semigroup for the S gamma that I worked just before. This is a new perturbation, and you apply again the Joubel formula. You obtain a solution which will give, which is given by the usual fixed point argument, and then you can obtain your existence result from where, if I think I've 2 minutes, 1 minute, from where you can obtain how do you obtain the lower bound estimate? So you have the initial data for which you know exactly the behavior as t goes to 0 and X goes to 0, which is given essentially by these two first terms. And then you get this extra term coming from the perturbation of the operator R. And that is the term that you need to control. Now, that term is non-local. Okay. But if you control the L1 norm of F, and that's the hypothesis you do for the corollary. If you control the L1 norm of F, you will control the L1 norm of this term. Now, if this term is in L1, if this term is in L1, and if you suppose that F is also in L1, you get a contradiction because this guy cannot be in L1 of any small interval. So that's where the contradiction comes from. If you suppose that F is in L1, this quantity here will be in L1. And then this guy, if this is strictly positive, of course, this guy will be in L1, and that's impossible. So that gives you a contradiction. And from there, you deduce the instability result. And I hope that's something I'm still working on, but everything shows that you will not have integral solutions for the nonlinear problem. So thank you very much for your attention. I think it's time to finish now.
Thank you very much, Miguel, for the nice talk. Now it's time for questions or comments. Yes, Enrique, please.
Okay, thank you, Miguel, for the talk and for so many things, right? So many years. So thank you. So finally, the conclusion is what? Is you do a linearization, you get L1 solutions, but then when you go back to the nonlinear, they are not.
You cannot get L1 solutions.
But for the linearized, you do.
No. You get solutions that are in L1 with the weights.
Oh, with the weight.
X alpha times F is integrable, but not F.
Yeah. And then once you have the linearized, you have understood the linearized problem in these weighted L1 spaces. In the nonlinear case, what do you get?
So in the nonlinear case, I'm still finishing it, but I suspect strongly that you will not have L1 solutions. So the impression is that the equation is bad behavior as soon as in the neighborhood of this maximal steady state. Okay? If you perturb this steady state to get something bigger or with a higher number of particles, the equation is bad behaved.
So there is no way of giving a sense to the solution after beyond this
even to define the weak formulation. You see, you need to do some. You need to apply Fubini, just like in the PDEs. You need to do some integration by parts.
Right. Maybe there is some renormalized thing or something like this. Yeah. And what do you, if you look in the PDE setting, of course, for PDE people, the PDE looks nicer, although we see these ugly weights, right? X squared, X4, and so on. If you look at the problem in the PDE setting, do you see any better? I mean, you understand better?
The PDE also has a problem.
Is that what? It's a boundary condition at X equals 0, or what is the?
Yeah. So I don't know how to go back. So let me see if I'm able to go back in this. If one goes back to the PDE.
No, you stop sharing your screen, Miguel.
Yeah, this is the strong solution to go back. Right? So
it's a strong solution. So if you go back to the PDE, you see there's a convection term, this du square over dx, that is pushing everything towards the origin. And in finite time, you lose. If you want to look at the PDE, you need some boundary condition. So the natural boundary condition is to put something that preserves the total amount of particles. So the integral of the right-hand side is 0.
Yeah, so some flux condition, right? Yeah.
And this condition is lost in finite time.
Okay.
Because everything is, so you get a very strong gradient near the origin. And so X square times du square over dx is too large, and so not for all the solutions, but a lot of solutions you will lose the boundary conditions. So,
and is this related to being, say, near this maximal steady state, or this is a completely different phenomena? What you are telling now about
it's probably related, because you also need to be very concentrated. So as the impression is that as soon as you have strong gradients near the origin, your solutions will have, you will have problems. So in the PDE, you can solve the problem, because the PDEs are much better, of course, as we all know. So you can solve the problem. But in the case of the Boltzmann equation, I don't think that you will be able to solve the problem.
And so the way, so there is a kind of subordination of the PDE to the Boltzmann, but you cannot go back, or you do?
So if you assume the relation is not complete, so it's not very clear. If you suppose that if you regularize the kernel omega that I wrote, that omega function, and you put something that is regular, then you can expand, and then you can prove that the solutions converge to the solution of the PDE. But you need to impose a lot of conditions. In particular, you need to have a regular kernel.
And what kind of technique you use to pass to the limit? Is again some kind of Fourier or
no. In that case, is there is a small parameter in the Boltzmann equation that I didn't wrote because I wanted to simplify. There is a small parameter which depends on the temperature of your gas. So when the parameter goes to infinity, formally your kernel goes to a Dirac measure along the diagonal x equal y in the integral.
Okay.
And so formally you converge to something which is a diffusion equation.
Okay.
So what if you replace the kernel I wrote by something more regular, and if you take a good initial data to have regular solutions, then you can pass to the limit.
But pass, I mean, in the functional sense, right? Not only formally, but in a rigorous setting. Yeah.
But you need to impose a lot of regularity conditions. Okay, so I don't see how you can expect something like that with a real physical. But it's not very surprising, because the equation is you have neglected a lot of phenomena in the physics, and so probably the equation is not robust enough to consider all the possible cases. So if you are below an equilibrium, everything goes well. You have everything is bounded, regular. So the equation is. But if you get something too large somewhere, or then the equation seems to have a problem. So that's my impression.
Okay, thank you, Miguel, again.
Thank you. Are there any more questions or comments? No? Okay, so thank you, Miguel. Thank you again.
Thank you.
And we'll restart in 7 minutes with Rafael Orive. I think he's there, yes.
Do you listen me?
Maybe we can start. You don't
You listen me?
Carlos? Yes.
Okay. Let's move. Do you see the presentation?
Yes, very clear. So we give 2 minutes if somebody connects
Only.
or talk.
Do you see the next page?
Yes.
Okay, perfect. No problems.
Okay, so we resume now. So it's a pleasure to present Rafael Orive. Rafael was one of the Enrique's students, so he's my brother, I will say, but also he was a student of Carlos Conca. And so he get his PhD at the Universidad Autónoma de Madrid and at the Universidad of Chile. And he's associate professor in applied mathematics at the Universidad Autónoma de Madrid. He's also a member of the Instituto de Ciencias Matemáticas since its creation in 2007. So he's going to talk about the spectral gaps in planar waveguides. So thank you very much, Rafa. No, your microphone is closed.
You are mute. Okay. I have a microphone. Yeah. First, it's a pleasure to me to participate in this Congress. I thank to the committee for this invitation to participate. I know Enrique 25 years ago, too much time. He was my professor in the last year in my graduate students in Complutense. I knew this year I met Enrique changed my life. No, I began my students with him and with Carlos, and all this time was crucial for my career. And I think that also now is colleague, and of course it's a pleasure to me always talk with Enrique. Always I learn something with him, and of course I very thanks with the friendship with him. Okay, well, the talk is about the spectral gradient planar waveguides. It's a problem different of other areas that he worked in, Enrique worked, no? But there are a lot of relations. I told about them. Okay, this work is with Delfina Gómez, María Eugenia Pérez, and Sergei Nazarov. Delfina and María Eugenia was professors in Universidad de Cantabria, and Sergei is professor in University of St. Petersburg. Okay. Let me see. Yes. well, the weights, I think that Enrique, a lot of the works is about the weights, no? About also about the study of the eigenvalues, the asymptotic behaviors of the eigenvalues, etc. No? A lot of problems of control or asymptotic behavior is related with the eigenvalues and with the eigenfunctions. And this area now of my work is related with this thematic, with the asymptotic behavior of the eigenvalues. Okay, in homogeneous problems, the ways is natural to construct the behavior of the solutions. But in homogeneous media, the propagation of the weights are very difficult, no? Are very difficult to control, to study, because the behavior is quantitatively different than the homogeneous case. The reason is the scattering and interference of the medium is translated to the weights, and the behavior is more difficult. Okay. There are two areas of work about this thematic. The area that I work is in periodic media. In the periodic media, we can find the multiple scattering can manifest to obtain the stop bands or gaps in the frequency. This is very important because these gaps get passing down zones for waves where the waves not translate to other regions or stable solutions. This is to identify to the stopping zones. This is very important because these results is necessary to the different engineers, different applications engineers. For example, wide filters, wide dampers. This is very common for metamaterials, etc. Okay. In the disordered media, these problems are related with the Anderson localization. No? The Anderson localization says that in the random media or disordered media appear exponential localized models, in particular appear gaps in the spectrum. Well, what's happened? Well, the natural is the period media is almost one disordered media, or very near on disordered media, and with the periodic media is we obtain these situations, these gaps in the spectrum in particular. Okay, this area of work is very natural for Nazareth in the last almost 20 years. But there are other people like Baccarat, Borisot, Giuseppe Cardon, Hempel, Peter Kuzmin, Olaf Post, Rasolainen, Taskinen, etc. A lot of people, more of the Russian people, no, were in this area. Well, the problem that I study is easy. No? Well, is not very sophisticated. No? We study we work in some domain. This domain, like this, okay. This domain is a street. Is a street in all the real line, okay, and is bounded in the second direction in the vertical line. It's bounded always with side with size h, and we had a periodic design, one periodic design that in the vertical lines we had a lot of small holes, okay, only in the points that we translate with the integer numbers, okay. With these regions, we can define the periodicity there only with the domain 1/2 when the length is 1 in the h1 direction, and the length in the second direction is h. And in the center of the domain, we appear all the multiplied holes. All the holes are the similar, are the same design. No? This design is, in general, is a smooth function, is a smooth hole. It's possible to work with more sophisticated holes. Okay. In particular, is the problem, or the natural problem to work here is translate the problem in all the band only in the periodic set. Okay, I saw also it in the following problems. Okay, the spectral problem that we are working is the Laplace operator, only the Laplace operator. No, it's necessary to work with the other difficulties, and with two different situations, with direct problem in the boundary, or with the Neumann problem in the boundary. There, with these conditions, we obtain two behaviors completely different. But the analysis to work in these problems is with the same techniques, and the problem is appear that the results to obtain are completely different. It is necessary different techniques to obtain this. Oh, okay. The first result, well, we know, is the spectrum of these problems is a union or innumerable subsets, the connected bounded segments in R plus. These subsets are the bands. Is now the bands. Okay. What happened with these bands? Well, these bands is possible to intersect or not. In the case when no intersect, it's possible to appear gaps. Is one of the objectives of this problem. We study what is the limit of what is the limit, what is the behavior when epsilon is small in these problems. In particular, we describe the spectrum when epsilon is small. To obtain the structure of the band structure, it's natural to the classic. It's natural to use the Fokker-Planck transformation. Okay, in differential equations is the first author work in this Matemático was Fokker. He he worked in the theory of Floquet, and with this he obtained all the discompositions in the spectrum in one-dimensional equations of second order. For PDEs, the result is in the Passigal with Bloch and Delphi. The idea is a very popular idea. Sure that Carlos now saw these problems. Is the transform of Bloch transform that what's happening in the Bloch transform is we translate, we construct the solutions that translate by a way. Okay. With this for the function, the functions transform in other problem. This problem always is in the periodic cell. Okay. In this case, the periodic cell, remember, is the domain 0, 1. In the scale, in the variable is 1. And in the second variable is in 0, 8, and with the zeros, with the holes in the vertical line. Okay. In the Dirichlet problem, I had a Dirichlet condition in the boundary, and in the Neumann problem, I had a Neumann condition in the boundary. But in the boundary, that is the intersection with the boundary of the street. Okay. In the other part, the boundary of the cell, we put the quasi-periodic conditions. That is the necessary condition by the transform, the Gelfand transform. This saying that we have periodic conditions, but multiply by the way. Also in the derivatives and the derivatives of the functions and the functions. Okay. I use the classical formulation for operators. I need to work in particular space. In particular, I work space A's, but the space A's is the H1 space with boundary conditions Dirichlet in the region of the right of the left, and the other case, in the Neumann case, only is the H1 space, and also in two space is the quasi-periodic conditions in the vertical boundaries. Okay, I define these scalar products. I define the TS operator to traduce the operator to the problem of the Laplacian problem, and this I obtain this abstract equation, and the eigenvalues problems is traduced with other spectral parameter that this is 1 divided 1 plus the eigenvalue of the operators, or the Laplacian operator. Okay, with this operator is compact, the spectrum, the essential spectrum is 0. I have other discrete spectrum that correspond with the these eigenvalues that where we can get the eigenvalues of the Laplacian operator. with these eigenvalues, I have a sequence, the positive numbers. In particular, for Neumann problems, it's possible that the first eigenvalue with theta is equal to 0 is 0, but when it is positive, well, we know that this is positive, okay? And I have a continuity relation of this function of the eigenvalues is a continuity relation that depends on the parameter eta, and the support of this the image of this function is one of the bands of the spectrum, and this is with this obtain the structure of bands of the spectrum of the Laplacian, also in Neumann problem and the Dirichlet problem. Okay. The problem is now go to 0, epsilon go to 0, what's happened? The problems are completely different if I were in Neumann or in Dirichlet problem. First, I were in Dirichlet problem, and this is very nice. It's not surprise, but the limit of the eigenvalues for any eta of the band, converge always only one point in the case of the Dirichlet problem, and these points, these values, these real values, are the eigenvalues of the Laplacian in the rectangle 0,1 by 0,8 with Dirichlet condition in the boundary. Okay, if you observe, you remember the third problem. In the vertical line in 0, I have all the holes. I had Dirichlet conditions in these holes. The solutions are continuities, very near of the holes always is 0, and we can see in the limit that the limits go to 0 in all the vertical line. Okay, this in at the top, at the bottom, always is 0, and we can extend the problem, the solutions, by the structure of the transform of block transform. What happened when I translate 1? The problem what happened is 0 and 1, 0 in 0, 0 in 1, 0 at the bottom, and 0 at the top. In total, I had the rectangle with Dirichlet conditions, and the limit. This problem is very well known. The eigenvalues are numerables, and the eigenfunctions are signs in the direction in depend is 1, and signs by depend is 2, normalized by the structure of the rectangle, no? In particular, appear divided by a's because the rectangular in the h2 direction is the length h. Okay. Of course, the limit of the problems of the eigenvalues and the eigenvectors, in particular the eigenvalues is obtained, but the eigenvectors are different. No, it's not the solutions of the Dirichlet problem. The eigenfunctions of the domain with the boundary conditions in the vertical lines in 1/2 and -1/2, we have a quasi-periodic conditions. I need to get these quasi-periodic conditions multiplied by this number in one of the region. I can translate multiply with any factor, you have to obtain other formulation for the eigenfunctions. Okay. Also, we can see that the eigenfunctions depend eta. Okay. It's important also this result because I can get a strong stability of the convergence. The convergence, also the eigenfunctions and the eigenvalues can be when epsilon and eta go to epsilon go to 0, eta go to any eta. Okay, and in this case, the limited is the same eigenvalue, but the eigenfunctions depend converge to aquí eta gor, eta ja. Okay. With these results, it's not sufficient to get the Kath structure of the Dirichlet problem. I need to know what is the behavior or the limit for any eta to get this. In general, the eigenvalues there are some when epsilon go to 0, there are problems that eigenvalues disappear, are small but disappear and go to infinity. There are problems with different eigenvalues. It's necessary to get uniform rates to this convergence. Okay, to do this, it's necessary asymptotic analysis. I show now the principal ideas of this asymptotic analysis. We consider an ansatz with the eigenvalue. I think that my eigenvalue first is the homogenized eigenvalue, and also any function depending eta by multiplied by s. Okay. Equivalent, I had other expansion for the eigenfunctions. The first behavior is the homogenized limit, the homogenized limit obtained previously, and other function that multiplied by epsilon, and this function is necessary to see what is in particular this value also. And we are going to do a matching asymptotic, and to get it, we consider other expansion. This expansion is very near. This is the behavior very near of the hosts, and for this I need to construct some auxiliary functions that now I told about them, and there are some functions that depend on the derivative of the homogenized solutions in 0 and 1. That remember, the homogenized solutions go to 0 when x1 go to 0, and go to 0 when h1 go to 1. Okay, and these solutions depend also the way of the periodic boundary conditions in the vertical lines. Okay, well, the WB plus minus are solutions of are harmonic solutions, but are harmonic solutions in some special properties. I need solutions with some behavior in the limit when h1, the modulus on h1 go to 0. The behavior of these functions as periodic condition in the direction h2 with these periodic conditions is necessary to work in the periodicity there, and in this case we need that the Dirichlet condition in the boundary of the hole. This is the problem is in all the street, okay, in all the for any x1 in R. Okay. The theory say us that there are two solutions. Well, the solutions of these problems are combinations of two solutions. These two solutions are WB plus and WB minus, and we can construct the behavior of these solutions. In particular, these solutions, okay, is linear in infinity because one function, WB tilde, is with exponential decay. Also, C1 go to infinity or C1 go to minus infinity. And in infinity, this is the behavior is like the C1 derivative, and is necessary some constant positive or some constants in the direction 1, in the direction positive, and in other constants in the direction negative. In particular, is linear in the one direction, in H1, in H1, in positive H1, and is constant in the behavior is constant in the other in the negative direction, and the other function is the contrary, is linear in the negative edge, and is positive in the is linear in the negative edge and is constant in the positive edge. Okay, and all the solutions are combinations of these functions. For these solutions appear some coefficients. Is now the polarization coefficients is two matrices that the behavior of the constant behavior on the right on the left. Okay, with this these constants are very important to get the size of the gas. Okay, to obtain the estimates, the uniform estimates, we need some classical result. This is the classical lemma of near eigenvalues. This lemma say that you construct some function u epsilon star or u epsilon h, and some value m epsilon to get that I apply to this function to the operator, to the abstract operator, and the difference of these things in the normal or in the norm of the problem is small, and I can estimate this rate. When as a consequence of this, there is some eigenvalue that the distance, the eigenvalue to this value that I construct is the same rate that the estimate with the difference. Okay. Well, the values that I use is the two terms of the asymptotic behavior of the eigenvalue, and the function is a collection of different different functions that the homogenize the solution, the U1 solution, the U1, and the inner functions of the asymptotic analysis. Well, these functions, I obtain this estimate. This is important, but this estimate is for any eta of the domain, any eta of the dual problem, and depend the sun constant and depend for any epsilon sufficiently small to get this estimate for any n. Okay, these constants and these epsilons depend the eigenvalues when I work. But other consequence that we obtain, that is not trivial, is there are no seeds other eigenvalue that satisfy this. Remember that the lemma say us there exists some eigenvalue, but this eigenvalue is not the unit. But we can obtain that this eigenvalue is the unit. This is for consequence of the strong stability of the convergence that we have for this problem. The value of the function lambda 1 is now and depend of the coefficients of the matrix of polarization. Okay, and also depend the derivatives of the eigenvalue or eigenvector or the homogenized eigenvector. This is natural in all the in general in all the problems of the homogenization, but this coefficient are different than other situations. Okay, I have some relations with the coefficients. I have properties, but it's not important. But it's important to get values to the length of the gap, no? In particular for the structure of the eigenvalues. Okay, remember, yes, because I take some eigenvalue in particular. This eigenvalue depend to values. The n is the respect to the derision h1, q is the depend of the derision h2. With these values, I know what is the eigenfunctions, and I know what is this parameter. This parameter depends the cosine. The cosine, the maximum value is positive, is 1, or the minimum value is -1. Multiplied by this number, we can obtain the maximum value of this. In particular, I obtain that for this eigenvalue, the length of the eigenvalue only depend of the parameter in the one's direction. Okay, and the length of the gap is the other ratio. Similar analysis I can obtain with multiplied eigenvalues, but I must know I'm not the tool about this. But in particular, I have this picture to show what is the behavior that we obtain. No? In particular, I can obtain that any band is the order epsilon, depend the eigenvalues, of course. They are different, the order one with the other eigenvalues, because always are multiplies on natural numbers, divide the a's. This is also depend the a's. If this a's is very small or very large, the distance of the eigenvalues is more small. But with a's phase also I can construct this Gath structure for the eigenvalues. For the Dirichlet problem, the Gath structure is very easy to obtain. In fact, when the eigenvalues are multiplied, I have estimates I get estimates for any band. In particular, the sum of the bands is the order epsilon, and we happen the similar case where the problem is this band is possible that there are intersections in these bands. Okay. Well, for the Neumann problem is completely different, because the limit, the homogenization problem, or these eigenvalues is, well, disappear the holes. The holes, we can extend the solutions because it's the Neumann condition, no? And only have the problem with Neumann conditions at the top and at the bottom in the H2 direction, and the quasi-periodic conditions or the periodic conditions in the lateral boundary. Okay, with these conditions, the eigenpairs depend on parameter eta, and we construct a family of parabolas. This is parabolas, and now that's the curves of dispersion, and now to show in a picture now. And the eigenfunctions are what we know, but it depend the weights and depend the eta. Depend the eta with respect the direction is one. Okay. Well, the dispersion curves, I only work with in the region minus pp. Any parabola is the reflection with the HP and the A's minus P. Okay. This is one parabola, and the second parabola is at the bottom, because remember, the second parabola begin when n is one, and well, the first case is eta n equal to 0, and the second case is n equal 1, and is always is positive. Okay, this is for the second. Okay, here the first dispersion curves now depend the H2. The second dispersion curves depend the H2. Okay. Well, its H is sufficiently small, like the eigenvalues are divided by H. This dispersion curve is in the top, and it's more easy to work in this case. When this is the case when H is less than 1/2. The second picture is when the H is about 1/2 and 1, and the second dispersion curve go to the bottom and intersect the reflection, the first reflections of the dispersion curve, or the first dispersion curve. When the H is very large, the problem that appear is the dispersion curves are very near one of others. This is the first and the second. Of course, they are the third and too much. No, when I go to the limit, epsilon go to 0, there are the perturbation of the dispersion curves, and the result that I want to obtain in this problem is for when the second dispersion curve is out, is not in the regions that I can work, I can obtain gaps of the spectrum. In particular, I can obtain one gap in p squared, around p squared, another in around 4p squared. This is for A's less than 1/2, and when A's is less than 1, only I have the first gap. It's possible that appear others, because it's possible, for example, that this is go to 0, this is go to the bottom, this is go to top with different values of a's, appear other in other regions. But this is in a special case. Other possibilities is in the case when a's is very large, when this a's go to very near to the other. I think that when a's is very, very large, it's possible that obtain other gaps in this region. But this is problems. This is open problems for continuing to the work. Okay. Well, I don't know what time.
You are running out of time.
Okay.
In fact, so if you can finish, please.
I finish with very fast. I had the limits. I obtain some estimates. The problem that what happened is I don't have the problem of the lemma of the near eigenvalues is I don't identify. I know there are one eigenvalue, but it's possible there are other eigenvalues. Here there are a lot of eigenvalues. Is a problem. I need to work in different regions. I get some estimates in these regions. For example, in this box, I say that only I have one eigenvalue. And in the second box here, I have two eigenvalues. If I have one eigenvalue in this region, I can uniform estimates for this region. In the other region, it is necessary work with delta very small to obtain asymptotic analysis. I get asymptotic analysis. Okay, in the asymptotic analysis, I obtain that there are two eigenvalues in this region, and this is separate because I identify these values, and these values are sufficiently large. One of them. Okay. With these estimates, I can obtain the gap for this region. For the second region, I need asymptotic analysis in 4p². And finally, pues, I obtain the result of the picture. No, there. In some situations, I have two gaps. In other situations, I have other gap. When S is very large or more or less, is open problem to obtain more general case of gaps. Okay. Thank you very much. No, let me see. Thank you for the attention. Congratulations to Enrique for this birthday, 16th birthday. Okay, thank you.
Thank you very much, Rafa. Are there questions or comments? Please raise your hand. Or...
I have one question.
Hernan Oscar. Okay.
I would like to know about some application, physical application for the problem, for the connection, the classification. The theoretic classification with the physical meaning application. Also, I would like to know, see if possible, to obtain negative eigenvalue for another dimension. I know there are negative eigenvalue in another situation when the study manifold structure. Thank you very much for the aniversario, Enrique Zuazua, Hernán Cortés. Greeting for you.
Gracias, Hernán.
Muchas gracias también, profesor Zuazua.
Gracias. Thank you, Hernán. Well, for this case, the eigenvalues are always positive. No, it's impossible to get the negative eigenvalues. In other problems, for other operators, you can obtain the situation to. This is very natural to, well, very important to get for metamaterials and etc. It's true that I remember some paper with Carlos where we study in the behavior, the values in the homogenized problems. We study the tensor, the fourth tensor. In the fourth tensor, we obtain a negative sign. Do you remember, Carlos?
Yes. Perfectly. Yes.
In particular, this is the Barnett coefficients, no? I remember, no?
Barnett,
and
it's a four-order term. Yes.
Exactly. With this, in this case, for these problems, you can obtain this property, no? But for here, no, because always the bands are positives for the problem. Okay. These techniques to obtain asymptotic analysis is applied for different problems. This is the classical matching techniques, but are very, very complicated and very hard to work with them.
Okay, thank you. But
Yes. I have just one very brief comment to thank. I would like to thank Rafael for his very sharp result and strong result. He has been able to highlight new phenomena in the asymptotic behavior of the eigenvalues of homogenization problems. So congratulations, because there is a lot of things that I was not able to grasp in your presentation because I will need some more time, a lot of time, maybe. And congratulations also to Maria Eugenia and Delfina, because they have been working on this asymptotic behavior for a long time. And these results are quite impressive and very sharp. You have been able to measure the gap between these block intervals. This is the first time I see something like that. And the other phenomena that I would like to highlight is the fact that the convergence of continuous spectrum to something which is discrete. So we don't see spurious eigenvalues at the limit.
Yeah,
this is extremely surprising. This is the first time I see something like that.
Well, to get the result is not easy. I assume that this is for very special case, no? Well, also the domain is not homogeneous, no? But it's very symmetric. And don't have problems with boundaries or something, no? I remember the results of Gregoire or your problems, no? Where get these disappearing eigenvalues, no? Invisible eigenvalues. So I don't remember
spurious eigenvalues.
Exactly. Well, thank you for comments. Because yes, the one of the principal results of this problem is we study the homogenized limit. Well, the periodicity cell is a homogenized limit. In general, this is not the problem, because in general we work in the periodicity cell. In the periodicity cell is phase. No, here is no phase. Here is a other limit. No, we have double limit in this problem. No, we have one periodicity structure in the line in the horizontal line in periodicity 1, and the other periodicity is the order epsilon in this other periodicity, this other period structure is in the periodicity thing. And we need these auxiliary functions. I put only the auxiliary function that appear the polarization coefficients or in the work, but I need different other functions to make the matching, the correct matching. Is a very hard work. And all these ideas, or one of the principal ideas, are for Nazzaro. Nazzaro is a very special
yes, the Russian school.
This area is surprised that he worked with these functions without problems. It's incredible. It's incredible. And Delfina and Maria Eugenia, yes, fantastic girls, worked very, very well with me. I very happy with work with her. Okay. Okay.
So Rafael, we are looking forward to seeing these two papers published soon, very soon.
Yes, I think.
Okay, thanks again.
Much. Thank you very much, Rafael.
Can I add something, Lucero? Just a brief question. Okay, so Rafa, thank you for your talk and for how many years you say? 25 of friendship, right? Yeah. So yeah, you were very patient with me and also very courageous, right? Because I recall that you were a student in Complutense, and then there was this opportunity to go to Chile. I don't remember which project it was. And then we were looking for a brave young person to cross the ocean and go to Chile. And you said yes in real time, right? So as if you were born in my town, Eibar, right? So I see that in Burgos also there is some influence of yeah. Okay, so thank you for all these years of friendship and hard and excellent work. Just one question, Rafa, a bit stupid maybe. Of course, I understand the problem from a mathematical perspective, but my question was, so why an engineer would like to put holes on a waveguide? Is this something that is really done, or this is more a mathematical model? So I understand that, I mean, you will use perforations in many devices and designs, and in particular, to take advantage of the topology. But for waveguides, it looks like strange to put perforations, because this will probably end up trapping waves, right?
Mm-hmm. Well, in the applications to the engineers, I don't see the perforations. No, well, there are different materials that appear this structure. No, but I don't know if it's used to get the results. But there are other problems or similar problems, like for example in mathematics, I see that the electric materials with periodic conditions or with periodic behaviors in the line, with a very small structure in some special regions. No, it's not the same, but it's similar. And this is important, these materials, to get the interesting properties to the wave propagation, in particular to get the invisibility or something similar. Well, this problem isn't very nice, because the name, no, the street stands, no, because for the design of the problem, no, and always we work with the derivative of Neumann. The natural problem is Neumann, because the propagation is more natural to get Neumann conditions to continue the propagation than the Dirichlet conditions. No, the Dirichlet condition is very strong, but also it's possible to get not Dirichlet but almost Dirichlet. No, with mass concentrates etc. Then there are a lot of works, the Maria Eugenia and Delfina, for example. No, well, the this structure of the almost periodicity is very natural in different applications. No? Do you remember that these people in Valencia, no, that have a lot of structures to reduce the noise in the autoroutes, etc. No, there are a lot of applications. What happened? The engineers made the design. So the results of the reduce of the noise or the property that the people see, and it's okay. No, go out and patented this material is okay, and this is a mathematical problem, of course, and always in the mathematics. In a lot of cases, no, we are more slowly than the engineers, etc. No. This estimates this rates is not necessary for the engineer. No, have experiment, extend the designs and get the results. No, okay. Thank you, Enrique, for these years. I wait to visit to Germany, or I wait to visit here in Spain, because we are colleagues here. But I don't see 2 years for more time.
Yeah. I will see you soon, definitely. Thank you, Rafa.
See you.
Gunther has a question, but we are running
I just want to add to the discussion. So we were also working with Sergei Nazarov and Jari Taskinen on these bandgap structures. And in fact, with engineers, we talk in Erlangen. And when you come to Erlangen, you may want to discuss. I mean, you can also use elastic inclusions or even piezoelectric inclusions, and to produce these kind of bandgaps in real material. So there's good hope that this can actually be used.
True, it's true. Thank you, Lenny.
Okay, thank you, Rafa, again. So we continue with Alessio Porretta. Alessio is a full professor at the University of Rome Tor Vergata. His research activities mainly focus on convection diffusion equations, control, and Milford game theory. He has awarded the Miranda Prize for Young Researchers and the Fichera Prize. He has given lectures in more than 20 countries in the world, including courses on mean-field games held in Paris, Chicago, and ETH Zurich. His research papers collect more than 1,500 citations in math journals. He's going to talk about time decay of Fokker-Planck equations with confining drift. Thank you, Alessio. Can you share? Yes. No, I think I have to activate your microphone. Okay.
Okay, so I think everything should be fine with the, okay, so maybe I can hide here. Okay, so can you hear me and can you see the slides?
Yes.
Okay, great. Okay, so first of all, let me thank the organizers for this invitation. I'm very happy, and also I'm honored to be here to celebrate Enrique's birthday, and this gives me the opportunity to say how much I enjoyed actually my collaboration with Enrique. This was extremely stimulating for me, and really a big pleasure. And I only regret I don't have enough time to push all projects and all things that we could do together, but still we have time to do, of course, something together. And when I met Enrique, actually, I was much younger, and I also must say, as many other young people, how incredible aptitude that Enrique has with young researchers. And it's very rare, I think, for for someone of the quality of the outstanding rate as Enrique, to find someone like him who is always available to young people to discuss math. And then all our collaborations, I enjoyed them very, very much, and I learned a lot, and I'm still looking forward for other projects, of course. Okay, so okay, I must say that the topic today is actually a classical topic, but I must say where my interest comes from, and this is actually a sort of control problem. So this is a model coming from this mean field game theory. And okay, mean field game theory is a theory, I mean, suggested and developed around 2006 by Jean-Michel Lasry and Pierre-Louis Lyons, essentially to describe Nash equilibria in large populations dynamics. And so typically there is, I mean, the evolution of the population is described by a Fokker-Planck equation, where L is a diffusion process. It can be, I mean, just a Brownian motion with a drift term. It can be a non-local operator coming from a jump process. So it can be I mean, any kind of diffusion, I mean, process for the single agents, which describes the individual's dynamics. But the point is that this individual dynamics is then driven by the decisions, by the strategies taken by people, which in the simplest case is described by a vector field, which means that typically at least I repeat, in the simplest model, one can say that this population is driven by a vector field, which comes from the strategy taken by individuals to achieve some goal. Okay, so and this means that typically there is a Hamilton-Jacobi equation for the value function of the single agents, and as is customary in optimization, I mean, the strategy is typically described by the derivative of the Hamiltonian function with respect to the gradient, say, of the solution. Okay. And so typically here H is a convex function, and F might be some coupling cost depending on the population. So okay, so the typical mean field game system appears as a coupled system where you do have a Fokker-Planck equation where the drift term is coming, say, from the equation of the strategy of individuals, which of course contains also the adjoint operator L and the Hamiltonian term, and this is related to the cost the cost functional to the goals that individuals wants to achieve. Okay, I'm not entering here into really the mean field game theory because okay, I lecture many other times also in front of Enrique, and so I mean I will stick to a particular issue which is very close to also to one of my collaboration with Enrique, which is the long time behavior of this kind of systems. Okay, in general, what you expect in this setting is that if the coupling term here, if this cost is anti-aggregative and is smoothing, so which means essentially that people would rather be where the density is not big, the density, I mean, of the other agents, then it is expected that in a long time you might have this property, which is a sort of stabilization, which is a turnpike property, which might take this form that the solution U and M in time t are exponentially close to some stationary strategy, du bar, and some stationary, I mean, distribution of the population. And this, of course, does not occur at initial and final time, but it occurs essentially in a long intermediate time. So this is a property which is called turnpike property, and it was essentially one of the topics that I worked with Enrique, and actually the mean-field game long time behavior was exactly one of the goals and one of the one of the motivations for our collaboration, to discuss this property for general control systems. Okay, so we discovered many things with Enrique around the Sternpike property. Many other people worked later. Also, somehow I can say that this notion was a little bit revitalized, maybe by our work, and then there are many discussions later. But today, I would like to focus on a particular issue here, is that when you want to show this kind of property, you see that this mean-field game system, in the audience, you might not know anything about mean-field games, but certainly you will recognize here the structure of an optimality systems, okay? So you typically can recognize this system as a typical structure of, say, a state equation and an adjoint backward state equation. So if you want to describe long-time convergence, typically you need an interplay here between the long-time convergence of the Fokker-Planck equation and somehow the backward stabilization of the Hamilton-Jacobi. And in order to prove this kind of result, you definitely need some quantitative decay estimates. For example, this is just an example, you may need for a Fokker-Planck equation some kind of semigroup kind of decay. This is sort of coming from Duhamel formula, or you may need some global in time LP estimate, where you see those constant C is independent of the time horizon. Okay. So this led me so essentially to go back to the problem of the long-time stabilization of Fokker-Planck equation, which is the heart of this talk. And there is one crucial point here, is that in general, in this kind of situation, as is often the case in optimal control problems, you need very robust estimates. So, for example, you may need this kind of estimates for drifts which are time dependent, and you may not know, you may not have very much information on the drift B because it comes from the other equation. Of course, there may be some information that you may get here, but in general, you do not have explicit forms of drift. And this means that you really need a robust study of this decay of Fokker-Planck equation, or say decay. When I say decay, I mean long-time stabilization. So this is, I think that, all people who have worked in optimal control problems know very well that at some moment you need those properties of the state, maybe equation, or of course, or the adjoint state. And you need very robust kind of estimates that if you look for in the literature, maybe you are not able to find anything exactly in the way you need it. And so I think this is a very common motivation to go back and revisit even classical issues. So now I will so somehow extrapolate this problem. How do we prove, and what do we know about the stabilization of Fokker-Planck equations, so the trend to equilibrium? So this is a very classical problem. If you take a diffusion process and perturbed by a drift, and then you want to show that your solution, which is a probability density in RD, converts towards a stationary state. Okay, so this is not for free, first of all. And it is well known, this is related, first of all, to the ergodicity property of the process behind. Okay, ergodicity takes this form here, for example, is that the observation that you can take along the evolution of the process, which is the generator of this diffusion L. If you take the time average of these observations, then in long time, this average converges towards some observation, which can be just described by this stationary measure. Okay, this is a typical, it might be a definition of ergodicity, for example. And the mod, of course, this is not for free. If you consider the Brownian motion in RD, well, of course, this is, I mean, you need some property that enhance ergodicity, and in particular, this leads you very naturally to situations where you have not just a pure Brownian motion, but for example, an Austen-Uhlenbeck process, which means a Brownian motion plus a confining drift. Okay, so this is quite well known, of course. So a typical situation where you may expect this kind of stabilization in the whole space. Of course, I mean, you may consider results in a compact situation, but this is, I mean, this is less difficult and is induced essentially by compactness of the state space. Whereas when you are in a non-compact situation, like in RD, in the whole space, you need some property of the diffusion process behind, and in particular in this diffusion process L, or eventually in explicit form in the drift, you may need some confining property which says that the process does not escape to infinity. Okay, so this is all well known for the Brownian motion in particular, and it's convenient for my purposes to rephrase this problem in the sense of time decay for zero average distributions. Okay, what you do in linear problems, typically you have the existence of a stationary measure, and then you subtract, of course, the evolution and the stationary problem, and then you look for the stabilization of the semigroup for zero average distributions. Okay, so in this form, you may afford, for example, here in this kind of context, you now may discuss this decay properties even if the drift is time dependent. Okay, so now I'm trying to summarize what is known, for example, for the Brownian motion case, and what is known is that you have an exponential decay for zero average, say, distributions, for zero average solutions. So here, of course, this property is preserved, I mean, after integration by parts. And then, for example, for the Austen-Uhlenbeck semigroup, this is when the drift is sufficiently confining at infinity, you have this exponential decay. But if the confining property is a bit less strong, so typically this is for sublinear growth at infinity of the drift, then you might have a subgeometrical rate of convergence and, for example, polynomial decay. And I just want to mention it's the space X in which you are proving this kind of exponential decay is typically an L1 weighted space. This is very natural. We have seen something also similar in Miguel Escobedo's talk. When you are in this non-compact situation, well, there might be quantities which naturally enter into the game. And for example, a natural choice here will be some L1 weighted space, and the weights might be a power of X, which, okay, I'm using this slightly, I mean, modification of the power just to say that all the point here is at infinity, or the point of the weight here is at infinity. Okay, so this of course implies the decay in L1 norm if this power is positive, as it will always be the case, but as a price, and the price is that the initial distribution needs to have some finite moments, okay? Okay, so there is, I must say that there is a very huge literature on the stabilization of Fokker-Planck equation, and I will try to give my viewpoint on this literature. I actually learned a lot when I had to look at the literature, even if I could not find exactly what I needed, and so somehow I decided to go a little bit more deeply into this, the way things are proved. But okay, so starting from the classics, I would say, there is a very typical approach, which is a sort of energy and entropy methods, I would say, which most often applies to the case where the drift is the gradient of a potential. So this is related to variational methods. And it starts, I mean, since some celebrated results by Gross and then by Liggett and many others later in semigroup theory. So starting from the exploitation of the spectral gap in weighted L2 spaces. And this is related to the logarithmic Sobolev inequality. And this was essentially the proof given by Gross of the exponential decay of the Austin-Uhlenbeck semigroup. But then those methods had a sort of, upgrade or update, if you want, in the early thousands, in the early years of this century. And in particular, I mean, rather than discussing somehow the decay in weighted L2 norms, it was pointed out how natural it was to discuss the decay of the entropy or relative entropy of the measure of the solution M, relative again to some weight. And you see how, again, in both approaches, it's a very natural way to have weighted estimates. Very natural to have weighted estimates. Okay, so this kind of entropy dissipation methods were in particular developed by Giuseppe Toscani and by Villani, and they became very, very popular after the works by Villani, who was a wonderful, he popularized this method as usual in his wonderful way. And of course, there were many contributions, in particular by Markovic, and Carrillo used that a lot as well. Okay, so of course, this relies on functional inequalities like Poincaré inequality and logarithmic Sobolev inequality, and there's many connections with other important structural conditions like the Bakry-Emery conditions on manifolds. So it's very elegant approach, but there is maybe a drawback in my viewpoint, is that it's hard, first of all, to be generalized to very general diffusions, including non-local diffusions. So there are extensions to fractional Laplacians, but they already need quite precise forms of the drift. And so, I mean, even if those methods are very elegant, I would say that there is some drawback to have results in very large generality for the drift, in particular for time-dependent drifts, and somehow also for non-local diffusions. Then there is another approach by probabilistic methods, essentially, and I learned that from papers by Martin Ivern and Mattingly, but of course this dates back to much earlier works, in particular by Mine and Tweedy. And the typical idea of these methods is that if you look at the semigroup generated by, say, the Fokker-Planck plus the drift, then there are two properties which imply the exponential decay. So those two properties are the existence of a Lyapunov function for the adjoint operator A star. And you see, it does not need to be a global strict Lyapunov function, but just say a Lyapunov function outside a compact set. This is the spirit of this condition. Of course, I didn't mention there is a phi which is a Lyapunov function. So essentially, it goes to infinity at infinity. So it's a typical Lyapunov function, and it is a strict Lyapunov function outside a compact set. But then you also require the property that your semigroup enhance positivity in compact sets, like a sort of Harnack inequality, and that your measure is strictly sort of diffusivity property, you see, in compact sets. And those two properties give the exponential decay of the semigroup. And again, very natural space X is a L1 weighted space. In this case, the weight depends on the Lyapunov function. I must say that I like this approach very much. And then there are many developments later, in particular after this very deep work by Bakri, Catio, and Guillen in 2008. And many authors also mixed somehow the methods of the energy and entropy dissipation with this kind of approach by Lyapunov functions. And in particular, Michler worked a lot on that, and there are many contributions with many other colleagues. And these methods were also extended quite recently to non-local operators by Laflèche. Okay, so even if, of course, I mean, many ideas are already there, I am trying to suggest sort of a new approach, which is a sort of analytic. My opinion, it's more natural from the analytic viewpoint, so from the PDE viewpoint, rather than some of the ideas which here were taken essentially with probabilistic methods or with analytic but quite difficult argument. So I'm suggesting a simplification and a generalization at the same time of some of these ideas. So first of all, the point is that if you look back at this approach from the probabilistic viewpoint, you see that it combines two properties. One is a property of the adjoint operator, so it's the existence of a Lyapunov function, and the other is a property of the operator itself, which is a sort of preservation of positivity. When you are in applications, it might be difficult to check this latter condition because somehow it requires you to prove itself a new Harnack inequality. So it's clear that from this approach that those two ideas lead to the exponential decay. But when you, for example, need this for your specific problem, for example, in my case, I had this Minfield game system, and then I looked at my Fokker-Planck equation, and okay, I am not exactly in this framework. I must try to understand whether I do have this kind of property for my semigroup. It's not so straightforward. So I was looking for something which was somehow more readable and more user-friendly when you need something. And the first point is that my first remark, this is essentially more a remark, is that the decay of the Fokker-Planck equation can be entirely deduced by the dissipation estimates of the adjoint equations, so of drift diffusion equations. And what are this kind of dissipation estimates? Those are weighted oscillation estimates for the adjoint problem. So in this adjoint problem, so I have put it in the forward form. Of course, you can rephrase that in the backward form if you prefer. Of course, you do have the adjoint of your operator L, and you have your drift now acting in non-conservative form. And in this case, it's out of question that you have global estimates for the function u, but the ergodicity is observed in oscillation estimates. So the oscillation of u could be globally estimated once you do have an ergodic phenomena behind. And so I am introducing here a semi-norm for u, which is a weighted oscillation. And this weight is typically the Lyapunov function. And okay, you may just limit yourself to this case when you have a Lyapunov function of power type. And the typical result that I will prove in this case is, I just have here taken a sample case of the fractional Laplacian, which is a way to show you that this method applies to both local and non-local diffusion. And of course, the prototype is the whole range of fractional Laplacian, but does not need to be the fractional Laplacian. I'm not using at any level Fourier transform. This is can be extended to jump processes, which are not necessarily, the Poisson process or fractional, pure fractional Laplacian. Okay, and so what is the typical estimate I have in mind and I can prove is sort of theorem A is that, okay, you assume that your drift is sufficiently confining at infinity, and you have some other dissipative condition. I mean, this may depend whether you have a bit more of diffusion in the operator or a bit less diffusion in the operator, okay? And those conditions, so for example, if you take here the case of alpha above 1, this is the diffusive case for fractional Laplacian, and of course it includes the Brownian motion, the Laplacian case. Well, this is not very hard to check this condition, because essentially it says that your drift B can be just locally bounded in compact sets, and at infinity it is a bit dissipative. But this kind of dissipation is very much also, in general, in agreement with the property you already have required on B. Okay, and then the conclusion is that there exists an exponential decay for this semi-norm. Okay, an immediate consequence is the sort of corollary theorem B is that under the same assumption, the Fokker-Planck equation decays exponentially, of course, for zero average distributions. Okay, so I am not, now I will skip here some comment, but I will just give you the proof, which is, of course, a duality proof of the corollary B, just to stress one point. Okay, of course, I mean, I want to deduce the estimates for the Fokker-Planck from the adjoint operator. So it's clear that I am evaluating my Fokker-Planck equation along backward, say, solution of the adjoint operator. And then this is the only, say, the basic remark here is that, of course, since you are with zero average distribution, you are free to add any constant to the adjoint state. And here you just use your, say, your L1, L infinity weighted duality. And then you simply remark here, and this is something I learned from already one of those approaches by probabilist, is that it's very convenient. Of course, this is, once you think of that, this is, of course, an exercise, but it's convenient to remark that if you take just the infimum among all constants of this L infinity norm, then you just get the semi-norm that I introduced above. Okay, so this means that I can just minimize over C this inequality 1, and once I minimize over C, I estimate the L1 norm of the Fokker-Planck just in terms of the semi-norm of the adjoint operator. Okay, so okay, I must say I'm a bit confused with time, because since we started with delay, so can I ask how much time I do have?
5 minutes if you want.
Okay, 5 minutes. Okay, because we started very late, so I mean this confused me very, very much. Okay.
It's not like 5 minutes late, and okay, so. Okay,
I thought, okay, okay. I will try to shorten a little bit. Okay, of course, there are similar results for the slowly confining case, which means that the drift is a little bit less strong than the Ornstein-Uhlenbeck. And for example, and in this case, you with the same method, you deduce a polynomial decay. For example, this is I mean, a situation where if you use functional inequalities and so on, you have really to strongly modify the approach to go from say the logarithmic Sobolev inequality. You have to prove every kind of weak Poincaré inequalities to go from the, say, strongly confining to the slowly confining, while in this kind of approach, I mean, this is exactly, I mean, you don't need to change anything in the approach, except you just observe the different quantification in this method. Okay, so the main novelty, as I was saying, is that the decay of Fokker-Planck equation is entirely deduced by the decay of weighted semi-norms for drift diffusion equations. And if you rephrase this, so I'm trying to give you now a little bit more hints on the method, because you see this kind of estimate can be rephrased just by, okay, so this is equivalent to property 3, just rewriting the semi-norm, which is here. Of course, the weight now has been put in the right-hand side, so this is equivalent. But the main point here is that rather than proving directly 3, it's okay if we prove, I mean, the inequality for any bounded function psi of the difference of x minus y, of course, the distance between x minus y. Of course, if psi is bounded, this will be dominated by the Lyapunov function, so 4 implies 3. But the true inequality which you should observe in this kind of equation is inequality 4, for a reason which is probably clear if you reason in terms of interaction of your process starting from, say, x and y, because essentially this term psi takes care of the small range interactions. And while, of course, the long range interactions can only happen at infinity, and they are dominated by the Lyapunov function. So you see that in a single estimate, I am taking both properties that were required by the method developed by probabilists, in particular by Heirer and Mattingly. They were requiring that somehow you had this Lyapunov out of a compact set, and you had this preservation of positivity for the semigroup. But here, both properties are contained in a single estimate, because essentially when the difference between x and y is small, you have some diffusivity property which appears in this term, and you use the Lyapunov function for outside compact sets. So, so essentially, all the method that I am suggesting relies in proving this kind of estimates for general drift diffusion equations. And this estimate is in particular an evidence of ergodicity. It was also known somehow in the probabilistic literature with, of course, totally different methods. And if you want improving this kind of estimate with a purely analytic proof, this is also an extension of what was known to probabilists. And the key point, but here I'm really running out of time, is that essentially to show this kind of estimates, the key point is to give analytic versions of what I mean in probability is known as the coupling method. And this is something I had developed partially already with Enrique Priola in 2012, in particular for local diffusions, that essentially we had explained in our joint work that there was a sort of parallel, and it was a perfect translation between probabilistic coupling methods and the double invariables PDE methods. And revisiting these ideas and extending them to no-local diffusions, somehow you can also prove this kind of estimates in much more generality. Okay, so I will, of course, I mean, I had, I mean, this is just, I don't know if I have time, this is for people, of course, who never heard about coupling method. I can describe it very roughly, and the picture is maybe the simplest way. This is a reflection of the Brownian motion. So the coupling method is used in probability to say, if you want to estimate the expectation of the process starting from x and the expectation of the process starting of y, one of the tools they use is to reflect essentially this process and to build a new, what is called the coupling, so a new process in the product space, and to try to build this new process in the product space in the way to optimize the heating time of the diagonal. Because a coupling for probabilist is a process in the product space xy, so that when two processes, I mean the marginals should be the same, and then when this process in the product space hits the diagonal, then of course it remains there. Okay, so of course I can say more, but I see that I don't have enough time, so I'm just skipping to conclusions. Is that okay, I'm suggesting a new strategy for proving the long time decay rates of Fokker-Planck equations in much generality, so for local and non-local diffusions and for time-dependent drifts. And this is a way to recover and often extend, I must say, many results obtained with many different methods. So it's a sort of also unifying approach. And as a byproduct, this gives an analytical approach of many results which were only known, proved by probabilistic methods in this coupling method literature of probabilities. And of course, this was motivated by my joint work with Espen Jacobsen on mean-field games. Unfortunately or fortunately, I don't know, this is a byproduct of the lockdown period. We had not the opportunity. We were a little bit stuck with some of these estimates with Espen, and then okay, I decided to go more deeply in the literature, and then okay, I developed somehow this approach, and then of course this was very important for us to complete then our joint project on the turnpike property of mean-field games in many cases, including non-local operators, which had not been done before. Okay, so that's all. I thank you for the attention, and happy birthday again to Enrique.
Thank you very much, Alessio. So are there questions or comments? Enrique, please.
Yeah, so thank you, Alessio, for this beautiful talk. So what is the regularity you need on B finally?
Well, for B, you just can take a B which is L infinity in the diffusive case, and a little bit more in the say non-diffusive, or if you want, if that. So you see, let me just take the. Okay, so you see here,
right?
Just take as a prototype the fractional Laplacian. So when you have enough diffusion, so alpha is bigger than 1, you need two properties that can be formulated even for bounded drift. Of course, bounded at infinity must be coercive, must be confining, but the regularity, the local regularity, can be just L infinity, because I'm never using
kind of a one-sided Lipschitz condition or something like this, right?
Yes. If you want, there is some dissipativity on some part of the gradient of B, if you want. But you don't need, of course, the regularity to formulate this assumption. While you need a little bit more regularity here you need some regularity. Because this guy is bigger than 1, and this is because you lack a little bit of diffusion when alpha is below 1.
So actually, I'm asking you this because recently I was looking to references, but I didn't find much. Of course, there is a lot of works done for solving transport equations with non-smooth vector fields B, right?
Yeah.
The Bernal-Lyons and then many others after, right? But then when you look to the vanishing viscosity to understand how, of course, when the velocity field is smooth, it's very easy to understand what the vanishing viscosity does, right? It's basically you have transport and diffusion, right? This is what you say. But when the vector field is not smooth, I'm not sure there are results explaining how solutions behave as epsilon goes to 0 on the diffusion, right? Yeah. In a precise manner. Okay, so this is, but we can talk about this later. And then the final question, Alessio, was in this norm you have taken in which there is ux minus uy in the numerator and then x to some power plus y to some power in the denominator.
Yeah.
This space has a name, or where is this? This is not.
This is just. This is just a weighted semi-norm, if you want. And of course, I mean, if you have k equals 0 here, this is just the oscillation of u.
Right.
Okay, and then this is just a way of the weight enters at infinity. What is interesting, and as I said, I mean, I must say that when I found that, and then I realized, okay, that's true. I mean, you can prove this as an exercise, but it's important to notice here that this semi-norm is exactly the same as the infimum of u plus c in L infinity.
Mm-hmm. In L infinity, weighted.
Well, in this case, weighted because there is a weight here,
Yeah.
but of course
Yeah.
you can take the same for k equals 0.
And then in practice, what is easier is to deal with this differential quotient to the right, or rather with u plus c?
Yeah, okay, that's a good point, because I tried to show that it's very natural to get estimates in this semi-norm, and this is exactly what probabilists also were doing by this coupling method. So this is very natural for the estimates. But when you look at your adjoint argument for the Fokker-Planck, what you really need is this one. So the bridge, so it's, you see, because when you estimate the Fokker-Planck by duality, you essentially take profit of the fact that M0 is 0 average. And then what you see is that you have this 1 degree of freedom to add constants to the adjoint state.
Right.
So by duality, you would like to estimate that. But on the adjoint equation, the estimates come very naturally in this semi-norm. And then it's true that those two things are equal. And this is where there is a nice bridge. And or the argument, of course, is very, I would say, is very clear.
So do these seminars have a Fourier interpretation, or?
Wow, that's a good question.
Okay, but we can talk about this. Yeah, but yeah, probably there is something, right? Yeah.
Yeah, sure. Because, okay, of course, to be honest, if things were smoother, like if the U were smoother, if the drift was smoother, similar estimates can be obtained just by weighted gradient estimates.
Well, actually, in the case where B is just X, then
yes,
you
for
have
example,
explicit,
if B is X,
you know,
yes.
Yeah, the Hermite polynomials with Gaussians. I mean, you have a complete spectral decomposition, right?
Exactly. If you are in a smooth situation, you can find similar estimates just by looking at the gradient of U and looking at weighted estimates for the gradient. Okay?
Yeah, but then in that case, there is a clear, say, Fourier representation of the problem too. Yeah.
Yes, exactly. So this is maybe the link you were thinking of.
Yeah, definitely. Okay. Thank you, Alessio. Great talk. Thank you. Bye-bye.
Yeah.
Ciao.
Thank you. Please, Carlos.
Yes, thank you very much, Alessio, for your very nice talk. I have only a very simple question, because I'm not a specialist in this subject, but there is something which is not familiar for me in this identity of a norm, which depends on two variables, x and y. So this is a non-local term. For each value of x, you can see that y can varies all over Rd. And on the left-hand side, you have something which is local.
Yes. Okay, but yeah.
So on the right-hand side, you have something like what Enrique said, that it is some kind of Fourier norm, like in the space HS with fractional s.
Yes.
But on the left-hand side, you have something which is of a different nature.
Well,
of course, what you have on the right-hand side is must have plenty of advantage.
Yeah, of course, be careful that, of course, in the right-hand side, you don't have exactly, of course, say, an HS, because you see that you are not quotienting with the distance between X and Y.
Yes, of course, yes. It's
so this is,
different.
of course, this makes
X to the power K plus.
Yeah, exactly. So this makes somehow it possible. In my viewpoint, of course, I was looking at that by saying, this is the translation of view that you see the C is here, okay?
Mm-hmm.
So somehow, I mean, I'd not this, maybe you have a different viewpoint, as Enrique was saying, by thinking in Fourier, but okay, my understanding was, okay, I have the problem that, because in these problems, what we know already is that typically the gradient of U is, the oscillation is controlled, but U is not. So this means that you have this problem that your solution U can be translated here and there. And okay, so this is a way of saying that if you can somehow optimize among all those translation of U, and what you get in this optimization is a control, the best oscillation. Of course, this is an infimum. So you optimize among all this possible, say, translation of U, and this amounts at catching the best oscillation of U. So this is my viewpoint, but maybe it's different to your feeling. I don't know.
Thank you very much for your explanation. Yes.
Something more?
Okay, I will stop sharing. Okay.
Okay, thank you very much. So we start with, we thank you again. So we start with the next talk. So it's the other Enrique Fernández-Cara, who is professor at Universidad de Sevilla. He has a doctorate from this university and also from Paris 6. And his main areas of interest are the theoretical and numerical analysis and control of PDEs, with a special emphasis in nonlinear PDEs from physics, biology, etc. He's going to talk about controlling some PDEs with non-local in space terms. Thank you very much, Enrique.
Good afternoon, good morning, evening, good night. I don't know. I don't know if everything is all right. You see my slide? Do you hear me?
Yes.
Okay. Well, first of all, I want to thank the organizers for having invited me to this meeting. It's an honor for me to participate. And I want to thank deeply the invitation and the chance I have to speak a little bit about our common works with Enrique Zuazua and some other things. I know him since the 80s, and I have had the chance to meet him. I think that first in Paris, and then in Madrid and Sevilla, etc., in the old times. And it is. I'm going to say maybe things that you have already heard today, so it's not new. But I'd like to insist in two qualities that I have always appreciated in him. First, his ability to interact with everybody, and not exclusively on the mathematics he makes, but also in other areas of mathematics, and also, and overall, I dare say, his ability to make good maths in realistic problems. I think that this is a quality that he has maybe since he was collaborating with Jacques Williams. And I think that it's remarkable to
insist in the fact that it is possible to have an applied viewpoint of mathematics without renouncing to quality in analysis and quality in mathematics in overall. So I have the feeling to have been very lucky to work with him, and very grateful. He's more than a colleague for me, he's a friend. And I have only one regret, and the regret is that we have not been all the time close enough, geographically close enough to have worked more. But maybe there will be time to continue some of our projects in common. Okay, this is an old photograph. I will come back to some old photographs later. And I will now try to speak about some of his contributions, and some of them with me, but many others of her own, and on the control of PDEs. Let me make a small selection of, this is maybe a question of taste, some selection of his contributions that I think that still can lead to some new works. I will begin with an old work in collaboration with Juan Luis Vázquez, related to simple one-dimensional models of fluid-particle interaction, where they introduced an interesting idea that is written here. The idea is to use the lack of collision to ensure global existence, the lack of collision as a tool to ensure global existence of a nonlinear problem. I think that this is still something to be extended to higher dimensions. There is something there, in my opinion, that should give something for more realistic problems, in the sense that we can consider either two-dimensional or three-dimensional models of interaction of a fluid and structure. Anyway, I know that this idea has already been used in the world of controllability. In 2005, together with another Woba, we were able to deduce control results of these models. And later, many other colleagues have continued in these directions. There is a work by Liu, Takahashi, and Tuxnack, in which using an interesting idea, they were able to control these systems acting from one side. Later, there have been works by Muriel Bulakia, Axel Cés, and Muriel Bulaca, later with Sergio Guerrero, in which some things have been made in 2 or 3 dimensions, etc. Let me also enhance something that maybe has not been considered today, is the explanations and remedies that he introduces for the numerical ill-posedness of control waves, of controlling waves. As you know, when you try to discretize, to approximate the control problem for a wave equation, you have to be very careful in the choice of spaces, of approximation spaces. And I think that there is still something to do at the level of reinterpretation of these ideas. Maybe combining these explanations with the INFSUB conditioned by Bressy and maybe regularization processes for the numerical problem. And as a third selected contribution, let me speak a little bit about the sharp estimates we got on the cost of controlling heat partial differential equations in 2000s. It's written there, for general heat equations, we deduced a cost of the order of the exponential of C multiplied by 1/epsilon. And for the classical heat equation, we were able to go a little longer and to see that the cost is of the order of exponential of A over the square root of epsilon, in some sense an optimal result. And something that has been in the mind and in the work of several contributors since then has been to find the best constant A and to give an explanation of the geometrical characteristics that has to have such a constant in such a problem. As you see, there are still many open questions connected to the control of partial differential equations, and some of them are apparently elementary, but I like very much to present some examples of apparently easy or elementary problems that are not, in order to illustrate the situation. For example, we can ask a simple question: is it preferable to use cheap or expensive controls when you are trying to reach an objective? Let us look at a very simple situation, relatively simple situation, in which you have a finite dimensional system, an ordinary differential system of this kind, which is controlled by you. And let us try to do optimal control with a system of this kind. If you choose a functional like this one, in which P is symmetric and positive definite matrix, then implicitly you are deciding to use expensive controls, because you are trying to minimize the function in which the control, the size of the control, you don't care the size of the control. Contrarily, if you choose this other another function of this kind, in which you have added a term, epsilon multiplied by an integral in which U is explicit, R is another symmetric and positive definite matrix, then you're supposed to be trying to use cheaper controls. You care, you pay attention to the size of the control you are using. So the question is, what is better? To use J, and try to choose an optimal control for the system, or to use J epsilon or small epsilon? Evidently, you always have J of U less or equal than J epsilon of U. So you are going to get, from the viewpoint of the objective, a better result with J. But this is going to cost a little bit more energy. You will have to use a larger U to control, in this case, the system. So the good question is whether you have or not that the optimal value for the first optimal control problem is the limit, as epsilon goes to 0, of the second value of the infimum of J epsilon with respect to U. And this is an open question, in fact. In general, this is an open question. The answer is yes, if the system is linear in X, but in general, it is unknown whether or not this quality is satisfied. It is an interesting question also from the application viewpoint, because in the case of autonomous car driving, these are the kinds of systems you find. So in the autonomous car driving process, the control is the direction system and the acceleration system. So what do you prefer? To have very expensive systems and to get good results, or are you happy if you only use cheap systems and you get more or less the same results? Okay, this is to illustrate the kind of problems that we are going to consider now. I'm going to pass to the main subject of the talk, in which I will try to present some results concerning non-local in space partial differential equations of the parabolic and also the hyperbolic kind. The motivation of this kind of problems is the fact that many times you find non-local chemical effects on the temperature in a heat process, or non-local behavior of flux in the flow of the fluid, or non-local effects of the market in finance system, in finance model. And a typical kind of non-local term that you find is this one, an integral in space of a kernel K, usually depending on X and also psi, multiplied by the state Y. So the system to control in this part of the talk is this one. And I ask whether or not we are able to get null controllability. I mean, starting from an arbitrary y naught at time t equal to 0, with a control V, of course, supported by a small set little omega. Are we able or not to drive the solution of the system y exactly to 0 at capital T? As many of you know, probably all of you, this is equivalent to the observability of an adjoint. I mean, to prove this property, null controllability of the system is equivalent to prove an inequality that is written here for the solutions phi of a system of the same kind that is backwards in time and starts from an arbitrary phi t at capital T. So what we have to prove is an inequality, as usual, an inequality in which we are able to observe the whole phi, looking at the behavior of phi exclusively on little omega times 0t. Usually, when you are trying to do this for a heat equation or something like this, you use Kalman estimates. We use Kalman estimates for phi. And from the Kalman estimates for phi, we are able usually to deduce the observability. The Kalman estimates for phi say that the weighted integral of phi on the whole Q, on the whole set Q, is bounded by a quantity like this one, maybe weighted with an appropriate function rho. But here, Kalman estimates cannot be used, at least directly. If you try to apply a Kalman estimate for if you try to apply the usual argument to deduce a Kalman estimate for an equation like this one, what you get is something like this. You get a global weighted integral of phi bounded by what you want. That is a local integral of phi, also a weighted integral. But you cannot avoid to find something like this. Something like this that comes, of course, of the term that is here that sees all the behavior of phi in the whole omega. And it is not easy to deduce from an inequality like this one what you want, the observability estimate. So you have to do otherwise. In a result, in 2016, in collaboration with Enrique Zuazua and Q. Lee, we have been able to deduce the observability inequality under some particular hypothesis assumptions on the kernel K. Essentially, what we have asked to K is to satisfy this property. Once you write K as an expansion using the eigenfunctions of the Laplacian, the Dirichlet Laplacian on omega, you need these coefficients, K and J, to be small enough as M and J go to infinity. Small enough in an appropriate sense. Let me say that this smallness of the coefficients implies, in particular, that capital K has to be analytic. It's an analytic function with respect to x and xi. Under this assumption, we were able to prove the observability inequality that I have presented before. And I'm going to give now the idea of the proof. It is the unique proof that I'm going to detail, but I think that it is deserves to be presented because it is interesting to see why we have observability in this case. So we prove, in fact, that phi at time t equal to 0 is smaller than a local integral of p, where p is some part of phi. And this is still smaller than a local integral of phi. And what is p? P is the part of phi that satisfies the heat equation. I mean, I have written here phi equal to p plus zeta, and have imposed to p to be a solution of the heat equation and to satisfy the same final condition at phi. Okay. So this is the inequalities. These are the inequalities that I have to prove. For the inequality in the left, what we have done is to write that phi is the sum of p and zeta at 0, at t equal to 0. T equal to 0 is the final time here, in fact, because this is a system that is going, it's backwards in time. So this is the final time here. And I have written the composition of t equal to 0. And here, what we use is the energy estimates and the observability, the classical observability of P that are satisfied because P is the solution of the heat equation, to deduce that this term is less or equal than this local integral of P. And then we have used the energy estimates of zeta and again the energy estimates of observability of P to deduce that zeta at t equal to 0 is also less or equal than a constant that depends on k, the kernel k, multiplied by the local integral of P. Okay, so this gives this first inequality. The second inequality, which is the harder one, the second inequality is proved by contradiction. So let us assume that this is not satisfied. That we find a sequence of functions, Pn and phi n, for which we have these kind of inequalities. This is much greater than these other local integrals, so this is not satisfied. Then what we prove in that case is that zeta n, which is the difference of phi n and pi n, goes to 0 strongly in L2 of Q. This is the difficult point. The difficult point is to prove that if you have these inequalities, then the difference zeta n between phi n and pn necessarily goes to 0 as n goes to infinity. And here the key point is an inequality, an estimate that we got in 2000, in, a paper that we published a long time ago, that gives an estimate of the final values of the solution of the heat equation, of the backwards heat equation of this kind. In fact, this is an estimate that we got looking for other objectives, and it's an estimate that gives, if you look at it attentively, it gives the exact controllability of the heat equation in space that is larger, much larger than the image of the semigroup. In fact, the exact controllability of the heat equation in space that it's characterized by the finiteness of the sum that is here. So using this inequality, using the assumptions on K that have been imposed and the unique continuation of phi, which is the solution of this equation, I will come back to this in a moment. Using these three properties, we are able to prove that zeta n goes to 0. But if zeta n goes to 0, then again by the triangular inequality, Pn also goes to 0. And if Pn goes to 0, this is an absurd because we have assumed that these integrals were all them equal to 1. Okay. So the second inequality is also proved, and we have observability of phi. We have used this recently in a paper with Juan Limaco, Dani Nina, and Miguel Núñez to prove the local exact controllability of time t to a regular free solution of the system in the case in which we consider this heat equation with the coefficient, diffusion coefficient that depends globally on y. Before we had proved some time ago the null controllability, the local null controllability of problems of this kind, but now with the result that we have obtained in 2016, we have suddenly noticed that it was possible to prove also the exact controllability to any free solution, provided it is sufficiently regular and provided we start from a point y naught, which is sufficiently near. And the argument is not too difficult. What we have to do is to reduce the exact controllability to y bar to a null controllability problem for a system of this kind, and then to adapt the previous result and to prove that it is possible to find a control that drives z to 0, provided we start from a sufficiently small z naught. It is also possible to adapt this result to Stokes-like systems. It is not too difficult to do this. In fact, the argument is more or less the same. And it is connected to another argument that appeared in a recent work by Sergio Guerrero and Takeo Takahashi, in which the null controllability of systems of this kind is also proved by another method. And let me also remind that in the same paper in 2016, we have also been able to prove a similar result for the wave equation. The argument is more or less the same, even an easier argument works. And so it is a result that says that this equation is exact controllable. In fact, you can go from Z0, Z1 to any other W0 and W1 appropriate spaces with the control V localized at little omega, provided the geometrical control condition is satisfied for little omega and capital T. Let me make some comments and let me present some questions, some apparently simple but open questions for related to these results. First, let me mention some recent results by Miku, Takahashi, Pierlisi and Zuazua, Bicari, and Victor Hernandez Santa Maria, etc., where similar results have been proved. For example, in the case of the first of these works, the Burger's equation has been considered. Lisi Zuazua considered systems, non-scalar systems, and they proved a similar result about when the non-local terms appear, etc. Two questions. What happens when K is non-analytic? It's not analytic in X and C, in Psi. I said before that I was coming back to uniqueness. In fact, one of the ingredients of the proof that I have presented uses the uniqueness, the unique continuation of this equation. This can be asserted because K, essentially because K is analytic, as I said. A related question is for a kernel K symmetric and not necessarily analytic, whether we have or not the unique continuation for the eigenvalues, for the eigenfunctions of this problem. To my knowledge, this is an open question. Which are the minimal conditions on K to get uniqueness here? Another related question concerns this system. This is what is called the Burger's alpha system. This is an approximation of the Burger's equation, in which you have some kind of regularization of the velocity z. Z is the solution of a Poisson equation regularized through a parameter alpha. So it can be used as a regularization of U. And it is known that the Burger's alpha system is globally null controllable for any alpha. So it is a natural question to ask whether or not we have also exact controllability to the trajectories for any alpha, or at least local exact controllability to the trajectories for this system. In fact, you see that this can be written in a similar way as before, because Z is the solution of Poisson equation that can be written as an integral of the kernel multiplied by U. And if you replace here the value of Z, you find again a non-local, non-linear in this case, non-local parabolic system for equation for you. Okay, so this is another related question to my knowledge, still unknown. I'm going to finish my talk with some considerations on non-local in time partial terms. I mean, I'm going to consider now a particular system that is related to viscoelasticity, in which instead of non-local in space term, we have a non-local in time term that is, of course, caused by memory, by the presence of memory. This is the system. This is a very complicated system, the Aldrich system, in which you have a sort of generalization of the Navier-Stokes equation with an additional term, the divergence of tau. And tau is tensor, is what is called the extra stress elastic tensor. That is also the solution of an equation. It's a solution of a non-scalar equation that is hyperbolic and nonlinear. It's hyperbolic of first order. You don't have diffusion for tau. And it's nonlinear. There is a term here, g of gradient of u tau, that has this structure in which w of u is the antisymmetric part of the gradient of u, and d of u, as usual, is the symmetric part of the gradient of u. So it is nonlinear in the first special derivatives of u and tau. And of course, it is the source of all problems, of all theoretical and numerical problems for the solution of this system. This is very difficult, so I'm going to linearize the system at 0. And if we linearize at 0 the system, we find something like this. After substitution of the variables, we find something in which you recognize the usual terms of the Stokes problem, divergence of u is equal to 0, together with the memory term in which you have the second derivatives of u inside an integral in time. So the question is whether or not we are able to get boundary control results for a system like this, at least for the linearized system, 0, at least in this case. This is the scheme of the geometric domain in which you are trying to control the behavior of the fluid acting on a part of the boundary, gamma. And these are the results that we have. First, if we ask for a null controllability result for this system, the answer is no. It is not possible to control, to drive to 0 exactly all initial data U0 with a control F on gamma. It is not possible to do this. In fact, a result of this kind was already obtained some time ago by Sergio Guerrero and Danguillo for a somewhat simpler system. But if we ask for approximate controllability, then the answer is yes. For any epsilon, it is possible to control epsilon such that at capital T, the final value of u is distance less or equal than u1. Okay. It is interesting to know, to take into account that if one of the v is equal to 0, then we do get, in that case, we do get if b equals 0, of course, we have the Stokes system. We know that this is null controllable. And the same is true also, at least under the geometric control condition, if nu is equal to 0, because in this case, if nu is equal to 0, if you look at this system the good way, you recognize something like a wave equation with the pressure, something like, and this was obtained some time ago in collaboration with the Jose Luis Boldrini and others, and it's known that the result is also positive. Okay. Well, the proofs, of course, rely on classical arguments. It's again equivalent to observability, and it is proof that observability does not hold. So no null controllability of the system. And contrarily, approximate controllability is equivalent to unique continuation of the adjoint. It proves that the unique continuation holds using the analyticity of the solutions and some particular arguments. And I'm going to finish with mentioning other results very briefly, and final remarks and work that have still to do, some open questions. First, let me remind you that in the world of viscoelasticity, there is, since several years, also another strategy that relies on moving controls. Moving controls have been used by Felipe Chavez Silva, José Enrique Zuazua, and others to give a positive answer to the control of systems in which you find something of the same kind that we have seen. Something like a parabolic equation coupled to an ordinary differential equation or similar. It would be interesting if it is possible to extend these results to linear or to non-linear, to the original non-linear Oldroyd systems. Of course, there are many things to do still. In the numerical results, for example, to my knowledge, have not been explored for a moment. For moving controls or for approximate controls, it would be interesting to know what can be done. In the case of approximate control, it must be a difficult problem because notice that as epsilon goes to 0, it is expectable to have that the norm of the control goes to infinity, because in general we don't have no control. So this is a delicate problem from the numerical viewpoint, and in my opinion, this deserves some work. And I'm going to finish with a question that is pertinent, in my opinion. Said, in fact, for the original non-linear system. Remember that there is work by Jean-Michel Coron and in which it is proved that the Navier-Stokes equation is controllable, is locally controllable with one component, something that is not true for the linearized system. So it is not desperate to think that the non-linearities that we find here and overall in the equation for tau and make it possible to control, at least locally, this system. This may be a complicated question, but it is not clear whether or not non-linearity, non-linear systems are appropriate to control, controllable at least locally. Okay, thank you very much. Muchas gracias por la atención y felicidades a Enrique por su cumpleaños. I'm going to finish with the picture. In 2007, and I'm going really to finish with some words of a very beautiful song by Simon and Garfunkel, Old Friends, Bookends, says something like this. Long ago, it must be, have a photograph, preserve your memories, they are all that's left you. Thank you very much.
Thank you, Enrique. So are there questions or comments from Michelle?
Yes, thank you, Enrique, for this very nice talk. I'm not expert in this case whether it is kernel, but there are counterexamples to the fact that it may be not controllable for some k with yt minus Laplacian world integral from an omega k of xy and so on. Is there a counterexample or?
Sorry, I didn't hear. Can you repeat, please?
Yes, I was wondering if there are at least counterexample, let's say for k C1 or C2, to the controllability, to the null controllability. For the when there is the
in the case of the
yes, the integral of k.
You mean for the
non-local equation with the kernel A.
Excuse me, I didn't hear. Can you repeat again?
You have this result that if the k satisfies some condition with which implies analytic.
Okay. See. Yeah. No, I don't know. I don't know any counterexample. I don't know.
What happens if k depends on time?
What happens if k depends on time?
Okay. Well, k depends on time. You you have to be able to control the non-local term anyway. I mean, if k depends on time, then you can give a you can use usual estimates in order to control the integral. The problem is k depends on time and x in a mixed way. In that case, I don't know what to do.
Okay.
I don't know if you have k equal to something that depends on time, that can be outside the integral, then you can use it as a coefficient, and there is no problem to work with it. This is the argument used, in fact, for the controllability of the nonlinear system. In the case of the nonlinear system, you have something that depends on time, but it's outside the integral. The problem is that how can I say, if the dependence is more complicated than this, it's mixed, then you have a problem.
Okay. Thank you very much. Thank you.
In that case, it's not easy to speak. Okay. Thank you.
Enrique Zuazua.
So can you go back, Enrique, please, to the slide where you were talking about cheap controls and expensive controls? The limit as epsilon goes to 0 of j epsilon. So you said that that you know the answer when g is linear, right?
Sorry. Yes.
But okay. So even if u enters as a multiplicative control, right?
Yes.
Even if u enters as a multiplicative control, so if g is linear, you know how to do it. But if g is non-linear, you say this is not known.
This is
okay.
Point. This is in fact, this is a result. It is in the. There's a book by Blondel, and one there's a list of open questions for controls, and there you can find the result. The result is by Orlov, and it is very well explained there. Counter examples in control. I think that this is the title. Counter example.
Okay. It's very nice. It's a very nice problem, actually. It looks like very simple, so it's nice to look at. Good, excellent. So thank you, Enrique, for so many years of collaboration and friendship, and the great talk. And thank you all for being there so late, and the excellent journey. I mean, it was an excellent series of lectures, definitely. Yeah.
Okay, thank you. Do you have any other question or comment? Oh, I have a question, Enrique. You said that you have this non-controllability problem is not possible for the Aldrich equation or something like that. And I may ask if maybe it is approximate controllable, but not null controllable. So maybe is there a minimal time of controllability or something? You don't know.
Good question, in fact. It's a good question. I don't know. I haven't looked at this. I haven't looked at this. And I'm going to guess it's here.
I don't see it, but
I don't know. I don't know, but I'm not sure, because in fact, the argument that we have used in order to prove that this is not null controllable is that it's not possible to have observability. And if I remember well, we don't use here the size of t. I mean, if I remember well, for any capital T, we prove that it is impossible to have observability here. So I think that it is not a problem of minimal of having time large enough. I think that well, I have to see with detail, but I think that for the moment I think that it is not the problem with the size of T, but it is a good question.
Okay, well, thank you very much. So if there is not any other question, let's thank all the speakers of today and see you tomorrow.
Thank you. Hasta mañana. Chao.
Hasta mañana.
Good night.
Mañana, la madrugada para mí, ¿eh? They
bueno,
are
un abrazo a todos,
me to wake up very early. So have a nice day, afternoon. Bye-bye.
Good evening. See you tomorrow. Huh?
See you
tomorrow. Bye-bye.
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 Feliz cumpleaños a todos los colegas. Muchas gracias. A todos los cumpleañeros, porque todos son base 50 ahí, base 50, 60, ¿no? Everybody.
Everybody. Bye.
Okay. Bye.